Yes, sir. So, and actually, I have another doubt, sir. So,
Yeah,
whether the frequency excitations in the cars, sir,
yeah,
or the vehicles, it will be
yeah.
of high frequency or low frequency, actually,
It
sir?
is of broadband frequency excitation. That means, see, if you look at in this, no, see here you can see right at delta x 1, 2, 3, 4 point. So what are this represent is the undulation of the road surface. So this undulation of the road surface in the last lecture, you should remember that can be represented as a power spectral density function. That is what we have seen, right?
Yes, sir.
Yeah. So if we have a power spectral density function as a function of spatial frequency, and instead of considering the elevation profile, if you take its second derivative, acceleration, we have seen that it is till smaller range of frequency, a constant. After that, it is rapidly increasing. So this is what we have seen in the yesterday's lecture. So what does that means is this road undulation will excite a wider frequency spectrum. It will have from 1 hertz, 2 hertz, 3 hertz up to, it can excite of say higher frequency of 20K also. So it depends upon how smooth your road surface or the texture is. The smaller the wavelength, the higher the frequency. Higher the wavelength between the two peaks in the road, will have a lower frequency, right? So that is what essentially we have seen that the road can be. We will also see further on this. I will explain you as I explain random vibration excitation. But for you to answer now, if you look at, you will have the wavelength of the road from very small value to very high value. So very high value of wavelength multiplied by the speed will give you the low frequency excitation, and the low value of wavelength multiplied by the speed will give you the higher frequency. So that is why the road will excite your vehicle with a higher band of frequency. But the system is so that the unsprung mass has got its resonance around 10 hertz. So what will happen? That excitation frequency will be picked by this, and this wheel will be hopping. Are you getting me? But however,
Yes, sir.
the road is going to excite not lower range. It will excite the energy with all the frequencies, broadband frequency, because the road is actually a random represented by a random variable, random function. So in such cases, it will be composing all spatial frequencies. So those spatial frequencies and the amplitude I'm sorry, can be obtained by applying Fourier transform and so on. But now looking at our simple model, the road excitation been picked by this unsprung mass of its resonance frequency. And this happens to be transferring the energy to the sprung mass. So excitation of the sprung mass is coming from the wheel vibration. If I assume, I can have this 2-degree freedom model can be further looked at a single degree freedom model. And for a single degree freedom model, you will have your transmissibility ratio is given by this. So what is this transmissibility ratio here is Z1 by Z2. So Z1 is sprung mass amplitude, Z2 is unsprung mass amplitude. And that is given here as function of excitation frequency by the sprung mass natural frequency. So if it is omega unsprung by omega sprung is the ratio here, and you see that ratio happens to be now according to this value is 10, which is which is very much here down. So the transmissibility ratio is very less. That means the energy transferred to the sprung mass is taken care by your suspension. As you have asked the question, and the excitation can also be from the lower range to the higher range, since the damping value of tire is negligible compared to that of the damping value of the suspension, the energy can be transferred even at low frequencies to the sprung mass. It is unrestricted. In such cases, your road condition is such that it goes over the disturbance where it can get excited at this low frequencies, and that energy can also enter. So that energy entering can be minimized by or controlled by the damping present in the suspension. So that is what is this explanation. Is that clear to you, Srisha?
Okay, sir. Okay, sir.
Yeah. So now that is not sufficient because here it is 1 degree freedom only. But I have to now design my suspension and I have to evaluate its performance. I cannot neglect the effect of unsprung mass. So I have to account that unsprung mass also into my study. If that is the thing, then I will have to get into my classical vibration analysis, wherein I will have to consider the unsprung mass also. Right, so the 2 degree freedom model. So now you see this transmissibility ratio here is Z1 by Z0. Z1 by Z0 is sprung mass amplitude of vibration to that of amplitude of road undulation, Z0. So that is given by this. So this A2, B2, C2 are coming from these equations only. Right, I have to substitute that in equation 1 and 2. I can get these ratios. Like you got it here, like you got it here. So this equation 11, 12 for natural frequencies you have got. The same way you will be able to get this ratios amplitude. Right. So continuing with that, if we look at if the damping of the shock absorber also is neglected, what will happen? Then your vibration model become free vibration model. There is no damping present in that. It is only sprung mass connected to unsprung mass by spring stiffness, and unsprung mass connected to contact with the road with the tire stiffness alone. So your equation further, this ratios here with the consideration of suspension damping, these equations 17 and 18 can further be reduced by Z1 by Z0 and Z2 by Z0, which replicate an undamped system. And wherein here you can see the equation omega n1 and omega n2 equation 19 and 20 in the denominator. They are essentially undamped circular natural frequencies, which we have been obtained in the free vibration analysis earlier. And this omega here is what is an excitation frequency. So this excitation frequency is obtained how? It is, this excitation frequency is 2 pi f, where f is the excitation frequency in hertz, is given by velocity of the vehicle multiplied by velocity of the vehicle divided by the wavelength. Velocity of the vehicle is meter per second, wavelength is a meter. If you divide, what is that you get? 1 per second. So you get small f. So 2 pi small f in here is what is your excitation frequency omega here. Right? Is that clear?
Excuse me, sir.
Yeah.
Hello.
Hello. Yeah.
How are we going to account? Yaw motion, roll, and pitch in the vibration model?
Yeah, that's a good question. But see, now we are now with the model which is quarter car model, which is only considering an important motion of the sprung mass called bounce motion during its vibration. As you have asked rightly, the question, how are we going to account the pitch and the roll effect? We have another mathematical model, which I have explained, shown you the model alone in the previous lecture. You can also see the previous lecture notes, where those models are separate, called pitch and bounce model or bounce and roll models. Right? So we will look at one by one of those effects with the different models. So if I have to account all of them, then it is again full car model. So full car model means degrees of freedom will be more, and it is not easy to handle the equations and to manually work out. But however, they can be studied independently. So that is why we consider now the quarter car model for the today's discussion. We will see, of course, pitch and bounce model in the next class. Am I clear to you? Or is it clear to you?
Fine, sir.
Yeah.
Yes. Yes.
So going ahead with this now, after getting this expression till 20, Z1 by Z0 is the transmissibility or the transfer function. If Z1 is an output, Z0 is an input amplitude that comes from the road elevation. Similarly, Z2 by Z0 is that amplitude ratio or transmissibility between unsprung and the road input. This expression. If I go ahead with next slide, the overall performance of the suspension can be now more clearly quantified or understood. So the suspension primarily has got three important functions in a vehicle. That is, one is vibration isolation, suspension travel, and road holding. So what do you mean by vibration isolation is what exactly so far we have been discussing. So I do not want a higher amplitude of vehicle body, right? So that is what is going to provide a better ride, a better comfort level the vehicle, right? Sprung mass amplitude of vibration should be minimized. So that is the objective of vibration isolation. What do you mean by suspension travel? Can anyone? What do you mean by suspension travel? Answer?
Bounce.
Minimum motion of the links.
Bounce and
suspension links.
rebound.
Bounce and rebounds. Yeah. So there is a space between your sprung mass and an unsprung mass where your suspension is employed, you erected, right? It is installed. So the spring will get compressed or elongated during the motion of the vehicle in vibration model. Your unsprung mass will be hopping. So you will have the effective space available between sprung mass and an unsprung mass is varying. So that space is what is called rattle space. You require that rattle space should not get reduced. The design requirement should fulfill that. So for that rattle space requirement, you look at the suspension. How does it going to provide you that? So that is what is called suspension travel. What do you mean by road holding? What do you mean?
Optimal downforce.
Huh? Yeah.
Optimum downforce.
Optimum downforce. That means you should have always road tires having contact with the road, right? So as this is vibrating, you should not lose the static deflection which is present in your tires diminishes. So when a vehicle is not moving and vehicle is not vibrating, what is the deflection of all the tires? It is a static deflection. So that is your static equilibrium position, above which your vibration of the system takes place. So if the static deflection happens to become zero during vibration, what will happen? There is a lifting of your wheel from the ground. So the holding of wheel on the ground is lost. So it should never happen during your motion. And that's what is important. So that means when you are doing hard cornering, obviously you see there is a load transfer, lateral load transfer from inside to the outside of the vehicle, inner side to the outside of the vehicle. So that makes the inner wheels to lose the normal. That's one thing that we have seen, rollover stability and so on. Even during the vehicle vibration and bounce, sprung mass bounce, what will happen? There can be a chance that the static deflection, what was there on its static equilibrium about which the vibration takes place, can go to zero value. At that time, you'll see there is lifting of your wheel, and that is that should not happen. That should be ensured. So that can be ensured again by means of what? By suspension. So suspension spring and suspension damping values can ensure that road holding also. So how these three parameters are quantified or is what we are going to see further. For that, if you see the influence of your unsprung mass, the influence of your suspension spring stiffness, and influence of your damping coefficient of the suspension. So these all three has got a role to meet these three objectives simultaneously. So that's what is that discussion that we'll see. And for that, I'm going to consider the same vehicle. What is that? Now we have considered the same unsprung sprung mass vehicle. What is that is here, right? This vehicle. this vehicle. So this vehicle data only we will consider, and then we will further analyze these results or try to interpret these results. So here again I have put that for your understanding that this vibration isolation can be evaluated by the response of the sprung mass to the excitation from the ground. Usually the transmissibility ratio, otherwise called transfer function, can be used as a basis for assessing the vibration isolation characteristics of a linear spring system. Why is it linear spring system? Because I'm going to consider the stiffness of the spring constant. So you see here there are three plots on this graph, on this slide, where I have a vertical axis common, transmissibility ratio. On horizontal axis I have the frequency kept here. So, right? So maybe this frequency range up to 14 hertz it is there, right? And you can see there are two peaks in every graph. So what are those two peaks refer to? One peak refer to the resonant point of sprung mass around 1 hertz. Another peak refer to around 10 hertz. So now if you look at for the given tire stiffness, so that is 176 kilonewton per meter, and if I vary this for the given tire stiffness and for the given sprung mass, if I vary the unsprung mass, right? So if ratio of unsprung mass is now like this given 0.05, 0.1 and 0.2. What do you mean by these values? If the ratio increases, that says for the given sprung mass, unsprung mass value. What do you mean by the higher ratio? Higher the ratio says higher the sprung mass, unsprung mass, higher the unsprung mass. Because the sprung mass is fixed here, unsprung mass value is less, then you'll have 0.05. If it is increases, it is 0.2. So the 0.1 is what is now a consideration of your vehicle data. So if it is increased, one value I take, if it is decreased, I'll take another value. So for these three cases, you look at what is the effect of this transmissibility ratio. So it is clear that below the sprung mass at low frequencies, it is not having any influence, significant influence. Whether I increase or decrease my unsprung mass, but decrease my unsprung mass means what? I can change the material of my rim so that the mass of unsprung is reduces. I can play around the mass value of unsprung mass. So by having lower mass and higher mass, what would be the effect that we have to see? That effect is nothing, insignificant in low frequency range. There is no separation. But if you look at the region closer to the unsprung mass natural frequency, you see that the higher, right? The higher the this graph, the higher the value of the ratio, higher the value of this ratio, you have below this 10 hertz or in mid frequency range. If you see up to this point, you have the transmissibility ratio is higher, whereas the lower the unsprung mass, is better because it has got low transmissibility ratio. Of course, if you go beyond the range of 10 hertz, you see that it's reversed. So you have the higher the unsprung mass is going to have lower the transmissibility ratio compared to that of this. So there is a penalty here, but it is preferred that if your excitation is in the mid-frequency range, lighter the unsprung mass is better for your ride because you have a low transmissibility ratio. Is that clear to all of you? You have a doubt now?
Hello.
Yeah, if you have a doubt.
Yes, sir.
Yeah.
Sir, transmissibility ratio more than 1 is good or less than 1 is good for ride quality?
Yeah, it's not more than 1, less than 1. It is 0.1, and this 0.1 ratio is what is the chosen vehicle. So I have
no, sir. Actually, in the excuse me, sir.
Yeah.
In the graph, hello.
Yeah.
I'm audible.
Yeah, audible. Go ahead.
in the graph on the y-axis at
Yeah.
a frequency of 1 hertz,
Yeah.
the transmissibility ratio is more than 1. The peak is showing that it is more than 1.
Yeah,
So
correct.
what is its significance?
What does it signify is if your excitation is of 1 hertz of unsprung mass, then you will have, this is the maximum transmissibility now, right? And that doesn't have any influence, that is not changed. See this graph says you can the energy excitation come from wheel is closer to 1, it cannot, correct? It is around 10 hertz only. But however, there is an energy transfer here. Even at the lower energy transfer can get amplified because of resonance frequency of the sprung mass. That is the meaning. So this peak here means that what is the maximum transmissibility value. So it is more than 1.
So it means
suppose the energy is
it
at
means
1
that
hertz. Yeah. Suppose the energy is at 1
so
hertz.
it means that it will
Amplitude
create more vibration than which is incoming, more
Yeah.
than what is incoming to the body.
Yeah, correct.
So means it is dangerous even at low frequencies.
Yeah, that is what is important. This at low frequency, you should not get excited your sprung mass. Your excitation falling on this should not. That is why you should go for your further the third graph you see. You require damping value. You require tire stiffness value. So that is why you require spring as well as a damper. So here,
Dampers.
first graph is showing you for the given ratio of KTR by KS. So tire stiffness is greater than that of suspension spring stiffness. That is 8 according to the given data of the chosen vehicle. KTR is what is the tire stiffness for the given vehicle. The given vehicle sprung mass also is not changed. I just want to change my unsprung mass. And I know here the damping is also is constant. For this given value of the vehicle, if I just play around with my unsprung mass, what is that is going to happen is what I want to see. So for that, if I see, so this graph is something is similar to this graph. Here, what is that is there? That is this graph. Right? You see at 1 hertz, we have an amplitude shoots up. The energy cannot be unimpeded. It cannot be unrestricted. It can enter. If your excitation energy comes at these lower frequencies. Right? So this graph here is your parametric study. So if an excitation frequency happens to be 1 hertz, obviously you will have here having this suspension is of no, now the existing design is of no use and you'll have this higher amplitude. So it's on log scale, it is 1 and it is 1.1, 1.2. So 1.2 times it will be more only, you can't avoid. But your road texture is such that you ride on a smooth road. So on a smooth road, if you drive, your frequencies are not of very low frequencies excitation. It's all of higher frequency excitation. In such cases, you no need to worry. So your worry is of this frequency range comes. So when this frequency range come, you have this mid frequency range. So let us have frequency ranges of 3 for the analysis. One is 1 hertz below. Another one is mid frequency range 1 to 10. Another one is the third range is beyond 10 hertz. So mid frequency range, if you look at, if you have your lighter mass, it's better for transmissibility. So you will always have this operating condition in your vehicle on a smooth road, unless you drive on a road profile and a test track where you are expected to excite at 1 hertz and to make a quantification of reliability of your vehicle for ride and so on. But our road, highway roads are not constructed for this excitation, constructed for higher frequency excitation. So we need to focus on this. So the suspension, other thing will have its role here. Am I answered to your question?
Yes, sir.
Yeah. So now if you look at, so the 3 parameters that we take for all these 3 objective: isolation, vibration isolation, road holding, and suspension wheel travel. One is the unsprung mass. Another one is your stiffness of the suspension, and then damping value of the suspension. So looking at the second graph here, that is 7.10, you see here now that for a given same sprung mass, and the chosen unsprung mass to sprung mass ratio 0.1. That is for the given vehicle itself. Like here, this value. For these two given value, and the tire stiffness also is fixed, and damping value is fixed. I just play around now with the ratio of the stiffness. So see what is this ratio? Tire stiffness divided by spring stiffness of the suspension. So you know that KTR is greater than KS. So for the chosen vehicle, it is 8 times greater. For the data, from the data you can understand it is 8 times greater. So that is our base model. So if what is the value of phi refer here? Phi refer here, you increase the stiffness of the suspension because KTR is fixed. If you increase the stiffness of the suspension, the ratio 8 can become 5. If you decrease the suspension or you make a softer suspension spring, then the ratio can increase. So these are the three conditions that we look at the variation of transmissibility as function of frequency now. If that is so, if you look at now the first range, that is below 1 Hertz, you see that which is preferred, a harder spring is preferred compared to that of the softer spring. But that is not the same case in the mid-frequency range. In mid-frequency range, you prefer a softer suspension spring. And you see the same here, the effect is less, but however, there is a penalty of that. So for the ride is concerned, if you have a softer suspension spring, that is better isolating compared to that of hard suspension spring. That's what you are understanding should be from this figure 7.10. Is it clear to all of you? Can I hear from someone?
Yes, sir.
Yes, sir. Yes, sir.
So we have another 10 minutes. We will try to complete this quickly. Hoping that you are following me and you are taking me. If you have any doubts, please pose the questions in the WhatsApp. So now looking at the figure 7.11. So what does this graph here? Look at this given data. Sprung mass is fixed. Unsprung mass to sprung mass ratio is fixed. Tire stiffness is fixed. And the ratio of tire stiffness to this is also fixed. So these all are fixed. So I'm going to only vary with the damping coefficient, right? So if I have the higher damping, obviously there is a lower amplitude. So that is why this graph, you see this is going like this. So the first range, we have, if we have a harder, means more the damping, better the isolation. In this range also, more the damping, better the, but the other two ranges, it is not so. So what is preferred in the other two ranges? If I have the damping coefficient less, see here the transmissibility is better. So I require low damper for low frequency. As that we have discussed here, most of the time your excitation is not at 1 Hertz on the highways. It is on these ranges, mid frequency and the higher frequencies. What is preferred here is, see this curve. So this curve is corresponding to the low damping value. So the low damping of the shock is better for vibration isolation in mid frequency and higher frequencies. However, it is not so at the lower frequencies. At low frequencies, it is vice versa. So I need to have hard spring. But that's what, this is the complexity. So to conclude all of this, if you look at for vibration isolation alone, it is always preferred to have a lower unsprung mass and softer the spring and lower the coefficient of damping is preferred for ride. So that is what is the conclusion. If you have to increase your performance of suspension for isolating the vibration that comes to the sprung mass. So going ahead with the next objective, suspension travel. So suspension travel here is defined as the ratio of the relative amplitude, maximum value of relative amplitude between unsprung and sprung mass to that of the amplitude of road undulation. So that is what you can see in this. So all the three graphs is for this objective of suspension travel. You see the suspension travel ratios are common in all the three graphs. We will have the same kind of discussion by looking at an influence of unsprung mass, looking at the influence of the suspension spring stiffness and suspension damping value. So, can anyone say that the suspension travel, what is the objective? Is that objective to be maximized or minimized? What is the value preferred? Can anyone? What is the value preferred? Lower the value. So, we require the lower the value of suspension travel ratio. Right? So, you can see that from this graph, same way, the varying the unsprung mass do not have any influence at low frequency. However, at the mid frequency and higher frequency, it has got its influence in an opposite way. In mid frequency range, you see that the lower the sprung mass is better for suspension travel ratio, whereas that is other way in the higher frequency beyond 10 hertz. All right? Yeah. And similarly, if you look at your stiffness requirement of the suspension, you see that you have a higher influence in the low frequencies. You see here, it's very interesting. So when it is 10, that means the softer the suspension. When you have a softer the suspension, you have your value here more. So here also, if you prefer softer suspension, the travel is more. The relative travel is more. So higher the suspension. So if you take the stiffness is higher, then it is better here. So what is preferred here is for a chosen frequency, you will have a value of this is minimum for the high stiffness spring compared to that of softer spring. That is for the lower frequency range. If you see that is getting crossover in the mid frequency range, and it doesn't have any significance in the higher frequency range. So if your excitation is of high frequencies beyond 10 hertz, so most of the time your excitation will be not even at 10 hertz in highway drive, because your wheel is not going to hop unless it is going over the bump and it is going to excite 10 hertz or 1 hertz. Otherwise, if it is a flat road you are driving, your frequencies all are not in this graph range. It is all out of the range. So it doesn't matter. It is not going to be much matter. But whenever you have some disturbance come suddenly, where your wheel hop is excited or these mid frequencies are excited, then it is very important that your suspension design. That's why we have this discussion. And then continuing with the third requirement, what is that is damping. You see the damping, higher the damping, the better it is for all the ranges. Low range or mid range or the upper range, it is better, right? So this is what is of suspension travel. Similarly, you can have a condition for road holding. So road holding is what is that static deflection of the tire. So for the given data, the static deflection of the tire is 3 centimeter. You can work out. You can get the sprung mass and unsprung mass for the ratio of 0.25 and then take total mass, take total load, divide that by the tire stiffness. You will have a value called value 3 centimeter. 3 centimeter for this vehicle is what is tire static deflection. If the tire static deflection disappears during wheel hop frequency, you will have a chance of contact loss. So the lower the value of this tire dynamic deflection, defined as the ratio of relative displacement of unsprung mass to that of an amplitude of road profile to that of amplitude of road profile. So this ratio should be minimum. This ratio should be minimum. So the similar way from this graph, you will be able to understand the significance of unsprung mass, spring stiffness, and the damping value. So unsprung mass, if you see, it has got an important role, not in lower range, it is in mid-frequency range. And mid-frequency range, you see that the heavier the value, heavier the mass is better. But again, it is contradicting to that of what is required for the ride. That's what is the critical observation here. Similarly, here you see mid-frequency range. So one can interpret in a similar fashion how we discussed earlier. And you see in the damping value, you have the damping value. The lower the damping value is, lower the damping value is not better, correct? So you see here the damping value, higher the damping value, 0.707 is better for this case of having road holding. So with that, I would like to conclude today's lecture. that this simple model. So though you do not require a vehicle of a high multi-degree freedom model, 2-degree freedom model, this bounce model, the quarter car model is quite sufficient to talk on the requirement of suspension design. So the influence of unsprung mass, tire stiffness, and the damping of the suspension are discussed in today's lecture to understand this. So I hope you have understood, and if you do not have any doubts, we will end the lecture, and tomorrow we'll look at another interesting model, pitch and bounce model. Right? Is that fine? Any doubts?
No, sir.
It is going to end in a minute. So if we have a question, you can just ask. Yeah. Any question? There are no questions.
Yes, sir. Sir,
Get over. Yeah.
sir, for ride comfort, actually, I had one doubt. I mean,
Yeah.
how is stiffer spring better and more damping is better for ride comfort?
Yeah. See, this is what this questions all to answer. This 9 graphs should be on your hand, and that answers you. So I think it's less than a minute. I will not be able to answer in this shorter duration. Let me end the meeting again. I will be available right now. You can join for your question. Right? I will end the meeting now, and you can join for the meeting once again. Those who have got a doubts, I'll. Right?
Yes, sir. Okay.